So
Excellent.
hello, everyone, and welcome to today's webinar on the perfect heat pump. I am Eric. My name's Eric. I'm the moderator. You're not going to be hearing from me until the Q&A portion at the end. Just to lead things off today, I wanted to let you guys know that we will be having a Q&A section at the end of the presentation. If you have any questions that you'd like to get answered, you can post them either in chat or by clicking Q&A. We'll be monitoring both of those. And without further ado, here is Tom to talk about the perfect heat pump. Tom, take it away.
All right. Thanks, Eric. And thanks to all of you. Sorry, I can't see who's who in this webinar the way I'm presenting. So if some of you are my friends, well, thanks for coming. And if some of you are colleagues, also thanks for coming. The title, The Perfect Heat Pump, is kind of on purpose misleading. It's closer to perfect, but it's still got a little bit yet to go. And one thing I do believe is that tech is going to keep improving, and it's going to get better and better. Maybe it's going to be this manufacturer, maybe some other manufacturer comes out with something that's way better. But right now, this one that I'm presenting is about as close as it gets. So, fun fact for you, and especially if you sat in the last webinar, things are changing when it comes to governments and climate change. So this is as of December 15th, in certain heights of high-rise buildings in New York, you're not going to be able, the owners of the building are not going to be able to use natural gas for heating, for their dryers, for domestic hot water. They're going to be all electric. So if you thought, this whole climate change stuff is a bunch of hooey and nothing's ever going to really happen, I think New York making this is going to get a lot of people's attention. Coming soon to the Midwest, probably not, but give it a little bit of time and it could. It depends on our political will. So heat pumps are going to be a part of all of our future, like it or not. So let's work on figuring out the best ones. So here we go. What are we going to cover today? Number one is, what would it do if it was perfect? And like I said, not quite there. But I assume most everybody on this call is living in the upper Midwest. And historically, heat pumps haven't handled cold climates well, and it should. So it would definitely handle cold climates. The perfect heat pump would perform better than the other heat pumps. And so we'll do a little bit of a comparison there. The cost would be comparable or better than a furnace and an air conditioner put together. Obviously, a big part of this is to manage our carbon footprint and the use of fossil fuels in residences, and of course businesses, but we're mostly talking about residences. They should be simple. They should last and last. They should improve your budgeting if you're the owner of the facility or the home. One big thing that we didn't talk about last time was, all right, let's say you wanted to put in a heat pump and, I got to change my electrical service at home. That's not going to be an incentive that people are going to want to deal with. And finally, the perfect heat pump should give the buyer a plaque that says, I'm helping save the planet. So with that, let's get started on item one. Cold climate heat pump should definitely handle cold climates. So I promise there are two sections that are a little bit nerdy. So put on your nerd mindset here. We're going to talk about sort of a challenging subject in the ratings of heat pumps. So one of the examples that one of the manufacturers I work with uses the NFL. And the NFL has rules, right? And who is the group of people that makes up the rules? Well, it's also the NFL, the National Football League. So AHRI is kind of like the same thing. It's this independent group that stamps and certifies what heat pumps do, how they perform, so on and so forth. So a heat pump needs to get certified by this group. Now, when you go onto if you ever decide to, which it is a very clunky website, there are over 100 manufacturers of heat pumps listed there. Now, there aren't really 100 manufacturers of heat pumps. There are heat pump manufacturers that get their stuff rebranded. If you do a different test, you can put a different sticker on the thing. You just got to pay for the test. So there's a lot of information on that website. If you just look at some of the majors like Trane and Carrier, they'll have thousands of listings of different combinations of heat pumps and coils and this and that. So it's interesting, but very nerdy technically. So if you were to pull up, now this is the listing for some of the Kinghome heat pumps. And as we're kind of digging in here, I want you to notice a couple things. I consider cold climate to be cold. I don't consider 17 degrees or 47 degrees Fahrenheit to be particularly cold. So what's interesting about this test setup is that in order to get a listing, you only have to test your heat pump at 47 degrees and list the output. Here's a lot of stuff going on here. Here's the name of the company that's being tested. This is the indoor unit. This is the outdoor unit. Hopefully you're all seeing my mouse. And then how much cooling capacity it has, what the efficiency rating is, what the SEER rating is, how much heat it puts out at 47 degrees, which you can kind of see here. A 36 is a 3-ton or 36,000 BTUs. It produces at 47 degrees, 36,000 BTUs. Because of the test setup, they lock the RPM. So even though this heat pump can produce 36,000 BTUs of heat at 17 degrees, it lists at 24.4. So already we've figured out that this standard heat pump test setup doesn't address all the cold climate concerns that we have in Wisconsin, Michigan, North Dakota, South Dakota, Minnesota, all that kind of stuff. So we need some additional test data to do evaluation. Hopefully you're still with me, that we haven't nerded out too far. Why is that? Well, I just want you to, this is a heat pump in the direction of, we're in heating mode here. So what's interesting is we have a liquid coming to our outdoor unit. And what we're going to do is boil that refrigerant liquid with our cold, we would consider it cold, -10 or -15 or whatever it is. We're still able to boil the refrigerant that's in this outdoor unit with that cold temperature and send it back. And then of course, we compress that gas and push the heat into the home. So unfortunately, now just imagine you're going to boil water on your stove, for example. Well, if you don't have a lot of heat, it's going to take a really long time to boil the water on the stove. So that's what gets challenging about cold climate heat pumps is as the temperature drops, our ability to boil the refrigerant goes down and down. So we need some additional test points in order to determine how well our heat pump's going to work. If our design temperature never got below 17 degrees, hey, we'd be fine. But we all know that it gets colder here. Milwaukee's design conditions are either -10 or -11. If we go over to Madison, it's -15. Green Bay's -15. Minnesota, I think, is -20 something. So it's colder than what the AHRI listings show. So a complete cold climate chart will have more temperatures. So we can see in highlights, these are the 2 temperatures that AHRI requires testing, and then they do some other stuff to lock out our heating requirements. So with the independent test that Kinghome has, you can see that at 2 tons at 47 degrees, it will produce exactly 24,000 BTUs per hour as it's controlled. And as we get colder and colder, finally at -15, we lose the ability to produce the entire load. Now, maybe the load isn't 24,000, maybe the load's 20,000. Well, then that heat pump can keep up with the whole load at -15. As we get to -22, we're thinking like Spooner, Wisconsin, or Duluth, Minnesota, our capacity goes down yet further. So some of these, sometimes we're going to need to get a little bit of help, but not until we get to really, really cold before we need some backup. Again, and like I said in the last presentation, as you change model sizes and you change manufacturers, all this data changes. So it's really important to know your heat pump and which size and what the load is. So I took a little bit of time to do some comparisons to other companies' heat pumps. Now, a heat pump is not just a heat pump. They're all a little bit different. So let's look. This one is a major brand. It's Carrier, and they make a nice heat pump. But as you can see, let's pick an example here. 25 to 30. This one looks to be, you're always looking for units that are in multiples of 6. So this looks like to be a 3-ton unit. So if we go across, well, let's see, as we're going down, our outdoor temperature from right to left, and reading backwards, you can see that the heating capacity drops as the temperature gets colder, just like I described earlier. But the amount of drop in capacity as temperatures gets colder is pretty significant. This top one, for example, can produce 72,000 BTUs of heating when it's warm outside, but it only produces, what is that? A third of that, down to -5. And then you'll notice that the graph stops. So what does that mean? Well, that means that they're not going to run their unit colder than the temperature that's listed here. So at -5, your heat pump, this version of heat pump is going to turn off. So you need a full backup in order to use the heat pump for part of the winter. All right, let's keep going. This one, I think, is Fujitsu, and they go a little bit lower, right? So I think this chart's a little bit hard to read, but I think that this -10 is in the middle of this area. So they're listing all the way down to -15, which is really cool. Unfortunately, they're giving us a pretty broad range of output, somewhere between 0 and 12,000. This is for a 2-ton unit. So when it gets really cold outside, you might get half the capacity and you might get none of the capacity. And this is the operating range. So would you feel comfortable if your home required or your apartment required 2 tons of heating, and some of the time it produced 1 ton and some of the time it produced 0, you'd be kind of out of luck. You'd need a lot of backup. Okay, this is a better still. This is, I think it's maybe Samsung, and at -5, it's producing, for 2 tons, it's producing, let's see, about 70%. But then they don't test any lower than -5. So if your design condition is -10, you're hoping for the best, and you really can't afford to do that. This one, Mitsubishi, is pretty well regarded as kind of the granddaddy of the heat pump industry, so I thought I'd do a little bit more time here. They have a product called Hyperheat. It doesn't, I don't know if this is a Hyperheat or not. This is the largest indoor central station. Kind of matches up with the product that I'm pitching. This is a 3-ton unit, and you can see that at 17 degrees, it produces about 2/3 of its capacity, which is not awful. It means you need some trim heat to back it up. But once it gets to 5, it's off. So this is also a non-starter for a single source, having the heat pump be the only source of heat for a home. So if your design condition is -10, in addition to the heat pump, you have to have a full electric or full gas backup. So you can't rely on the heat pump to do the whole shooting match. As heat pumps get smaller, they tend to be more efficient. They're more capable of producing an output, but these 1 ton and 1.5 tons are for pretty small spaces. And if you look a little bit more closely in their catalog, it's hard to find their data sometimes. But you can see that at -13, like, you don't have any capacity at all. At -4, you don't have much capacity. At 5 degrees, half the units are already knocked out. So this is really important when we say, oh, it's a cold climate heat pump, to look at the cold climate data if they have it. And if they don't have cold climate data, just assume it doesn't work in cold climates. So this is a chart, Eric actually said, Tom, that was an awful lot of data. How would you like me to keep tabs on this? So he said, make a chart. So these first 3 columns are 2 tons at different temperatures. This Kinghome unit at 2 tons. And remember, all the data changes as we change sizes. So this 2-ton unit at minus 15 still produces the full 24,000 BTUs. This carrier base model doesn't work. And when it's at 5 degrees, we've down to 1/3 of the output. Mitsubishi, no data. Fujitsu, somewhere between, at 5 degrees, it has quite a bit of capacity. I was surprised. LG does pretty well in some of these cold climate conditions. So those of you who are familiar with LG, it's a legit choice until you get to a little bit colder than -5, which unfortunately is Wisconsin, Michigan, and Minnesota. So close, and maybe they'll be able to find a way to bump it up. All right, so that was the nerdiest part of the presentation. If you're with me so far, I think you'll be happy that more of this is going to be in generalities. Okay, next, perfect heat pump. It would cost less than a traditional system. Okay, does it? So here's if you were going to start over, or I'm sorry, if you were going to do a full, let me back up. If we're going to do a start over, like we're going to clean out our basement, we're going to get rid of everything and start over. If I had, I'd buy a furnace, I'd buy an air conditioner. On top of that furnace, I'd have a refrigerant A coil, which is just basically, it looks like that, it sits on top of the furnace. We need a line set, we need labor and sheet metal. Okay, if I changed my mind, I didn't want a traditional air conditioner, I wanted a heat pump. Instead of that air conditioner, I'd buy a heat pump. Instead of that standard A coil, I would buy a heat pump A coil. They're almost the same thing. So what would my cost look like? If we buy the cheapest possible, the heat pump's going to be more expensive. If we start looking at efficiency, like if you recently looked for an air conditioner, the contractor would say, hey, let's give you an offer for 13 SEER, 16 SEER, 18 SEER, maybe even 20 SEER. As the contractor goes up in price, his labor charge is pretty much the same, but he's, I shouldn't say he, but the contractor is charging more because it costs more to get 18 SEER air conditioning, 16 SEER air conditioning, so forth. If you decide to go with the heat pump, ours costs about the same as a less efficient air conditioner. Our coil costs a little bit more than a standard coil. The labor is pretty much the same. Now, once we finally get this rebate, when we get our listing, I was showing you on AHRI before, you'll be eligible for a $1,000 dual fuel heat pump rebate. So your cost will be in between the cheapest of the cheap, the 13 SEER code compliant, and the next step up. So is it cheaper than the furnace and air conditioner? Depends on which air conditioner you buy, but it's pretty competitive. Not exactly the same. And of course, the labor may vary, depends on the contractor and depends on your install. But this is somewhere in the ballpark of what the truth should be. Something to keep in mind. All right, next. This is the second hardest part of the technical on this presentation. So just again, stay with me because there's a lot of digging that went into this. And I want you, when you guys say, hey, I'm saving the world by buying a heat pump, I want you guys to know really what that means. Okay, so this is a chart that if you do enough digging, you can find an intelligence chart. Hopefully you can read this, but what this says is emissions per megawatt hour. So what is that? That means how much carbon is being produced when we generate power from a power plant on the aggregate grid quality of every state. So in other words, in West Virginia, if you're going to burn a megawatt hour, it's going to produce more carbon, CO2, than if we're in Minnesota, and by a fairly healthy factor. Now, if you live in, let's say, Seattle, all their power is by hydro. So they produce almost no fossil fuel when they plug into their outlets or when they power up the heat pump. So where do the upper Midwest rank? Well, Wisconsin's kind of so great here. This is in pounds or tons of CO2 per megawatt hour. So we're not doing that great. In Michigan, our neighbor, is not so far, not so much better than us, but definitely better as a percentage. And look at these guys in Minnesota. Sorry you got knocked out of the playoffs, but you can definitely brag to all your cheesehead friends about how well you're doing with your grid, because it is significantly better than the grid quality by about 50% in Wisconsin. So what does that mean? If I plug in Minneapolis, I produce a lot less CO2 than when I plug in Wisconsin. Okay, so reminder, we've looked at this chart in past presentations. This is the power required to produce 3 tons or a maximum output for a heat pump. So as it gets colder, the requirement goes up or the output goes down at different temperatures and at different sizes. So let's do a little bit of math, just a little bit of math. From that chart, we can see that for every kilowatt hour, we produce 1.12 pounds of CO2. Now, for every 100,000 BTUs, which is kind of like probably what your furnace is sized at, it produces 11.7 pounds of CO2 for every hour. So to produce 36,000 BTUs of heat with a furnace, it's going to generate 4.48 pounds per hour, taking into account that your furnace is probably that efficient. So as you remember from this slide, the output changes with different temperatures. So how efficient does the heat pump need to be to produce that 36,000 BTUs in less than what it takes with gas? This is the changeover point that I'm trying to demonstrate. So unfortunately, in Wisconsin, the changeover point for switching from gas to electric is somewhere between 47 and 32 degrees. Why between those two? Because we just have those two data points. So at 4,000 watts, the change, you would be the same. You know, if it's, let's say it's 40 degrees outside and you use your heat pump or you use your furnace, it's going to produce about the same amount of CO2, which is kind of unfortunate because a lot of the heating season lands at 47 degrees and below. There's just some days that are 50 degrees and that kind of stuff. So we're not there yet with the Wisconsin grid. Now, let's look at Minnesota, which ranks 25th. Okay, same math, 4.48 pounds. When does the same heat pump change over to be more efficient, or I'm sorry, produce less CO2 than natural gas? And the changeover point is when it's much, much colder, between 17 degrees and 5 degrees. What does that mean? A lot more of the winter would be handled by a heat pump and produce less. As we go forward in time, the grids are going to get cleaner and cleaner, and this number is going to get lower and lower. This also helps to understand when you do your switchover for dual fuel, if you're going to use a furnace in conjunction with a heat pump. And finally, just that little bit of difference in Michigan. From, what was it? Wisconsin was 1.12 pounds, and Michigan is 0.953. That drops our changeover point all the way down to 32 degrees, which is much more of the winter. So way to go, Michigan. In Wisconsin, not so good, but we'll keep working. Okay, another perfect heat pump item. Simple to operate. If you're running a furnace and an air conditioner at home, it's pretty simple. This is what a standard heat pump stat would look like. It's either this handheld remote or this wall-mounted one, which is a little more intimidating than your basic stat. The heat pump that we're pitching will work with the standard Honeywell digital thermostat. Both these are available where you can use Wi-Fi to turn on your heat as you're driving home or whatever that turns out to be, but it's still going to be simple to operate. You shouldn't need a manual to figure out how this thing works. Okay. It should last. Yeah, it should. You don't want to buy a heat pump every 3 years. That would be bad. So here's the standard Kinghome warranty. Most furnace warranties are in par with this. I mean, there are some that if you buy the stainless steel heat exchanger, you can get 10 or 12 or 15 years or something like that. But it's 3 years for everything and then an additional 5 years in the compressor. So basically, it's like an 8-year warranty. Most heat pump manufacturers have something similar to this warranty, but I'd say it's pretty good considering the tech that's in it. You know, your air conditioner at home probably doesn't have a microprocessor in it and is less subject to lightning and that kind of stuff. Okay, moving on. It should reduce costs. In the last webinar, we went over this table, which shows that, hey, you really don't want to be using electricity to power your home. Hey, you really get a deal when you use natural gas. It's really cheap to run. When we switch to dual fuel, we get the benefit of the efficiency of air conditioning at a higher SEER, and we're not penalized so badly that there's a penalty for using the heat pump. So this is based on Wisconsin numbers, and we could probably spend another half an hour on this, but we did this in the last presentation. If you have questions, you can always email me and I can go through this with you individually. And I think we recorded the last one, which was, this part was towards the end. So annual operating costs, comparable, right? Comparable if we're doing dual fuel in the upper Midwest, but you can save a little bit of money. All right, fine, and moving on. This is just the math. If your 3 or 4 ton AC is 13, you just multiply this ratio times your costs, and that's what you'd end up paying, roughly. Okay. This is kind of a big deal. So let's say that you're doing a multifamily apartment, or you're going to be, you're building a house in a remote location. You're debating whether or not you're going to put propane in. All right. Here's a 100 amp service. In order to change it out to 200 amps, you got to disconnect every wire, bring more power out there. It's an expensive ordeal for, not the end of the world, but it's an expensive ordeal. Why would we need to put in more power? Well, if we're using our heat pump and it gets really cold, we may need some extra heat, some backup heat, right? So let's say we're building way north Wisconsin, for example, and it's a big house and it's 4 tons. We'll want probably 8 kilowatts of additional power just for when the heat pump's having a hard time keeping up when it gets really, really cold outside. And that's fine. That's a pretty manageable amount of electricity. Now, going back, we were comparing models before where these units turn off when it gets to be -5 or -15. Now, what do you need to do? Well, in those cases, and if you don't have propane, you got to put in a full electric backup. So here's side by side. Other heat pumps, a 2-ton system for full backup would require 7 kilowatts and 30 amps. So is there that much room on your existing circuit? I don't know. As you get to bigger and bigger systems, all we're doing here is converting tons to BTUs to watts. So 14 kilowatts required to fully back up a 4-ton system. And that's 60 amps of power. So you've already turned your 100 amp system into a 200 amp system, or your 200 amp system into a 250 amp system. However, with Kinghome, here's -15, for example, a little backup heat is 10 amps, 20 amps, 25 amps. You probably won't need to change your electric box out. You will need an electrician to do a little bit of work. So again, this is for all electric systems. If you have dual fuel, great. You don't need to worry about this. You can just run that heat pump whenever, and don't need to worry about electric backup. Okay, so we're going through this fairly quickly, but we're going to wrap it up. Going back to that original slide, that perfect heat pump, what could it do? Handle cold climates. Deftly. Well, other than fossil fuel, this heat pump is the best one that I'm familiar with. If you can find a heat pump that's better, great. That would be wonderful for everybody. Maybe not for me, but maybe we'll sell another one to somewhere down the line. Perform appreciably better than its competitors. In cold climate, this heat pump outperforms everybody I showed you by, I would say, a fairly substantial margin. The bigger the heat pump, the more the greater that gap grows. It would cost less than a furnace. If you buy a more efficient furnace plus air conditioner, it will, or it can. Reduce or eliminate the use of fossil fuels? Some, and it will to a certain extent. You people in Minnesota are going to be doing better than the folks in Wisconsin and Michigan, but I think we're going to catch up. Be simple to operate. It doesn't require a degree in refrigeration to operate a heat pump. It would last a long time. 8 years, I think, is pretty long. Most of our stuff lasts a lot longer. That's just as long as the manufacturer wants to manage a warranty. It would reduce operating costs. In the summer, it does for sure, because 18 SEER is way more efficient than 13, 14, or 16 SEER. And in the winter, sometimes it will. We don't want to have to rip apart our electrical. So depending on how much backup heat, if it's dual fuel and who you're using, it may be fairly manageable. Finally, it should include a plaque that would say, I'm helping save the planet. It does not, but maybe this is what it would look like. So with that, that's my last slide. We got through in about a half an hour. So we have plenty of time for Q&A, and I'll stop my share here and see if you guys have any questions at all. And I can, of course, bring that back up.
All right, sounds good. So just on a personal thing for the plaque, I'm not getting a plaque then?
No.
Okay.
Fun fact, Eric has a Daikin heat pump in his house, but unfortunately, he bought a furnace too, because he wasn't aware of heat pumps at the time. But I think I've heard you say you're happy with how quiet it is.
I am very happy with how quiet it is. Very, very happy with how quiet it is. So this is a great time if you have any questions to post them in chat, or raise your hand, or put something in the Q&A. So we do have a question here from Charles. He asks, what's the magic sauce? Why does yours work at -22 Fahrenheit and others stop at 5 degrees Fahrenheit?
Ooh, that's juicy. Will you give me just a second here so I can pull up a different slide?
Of course. And is it actually sauce?
Is it actually sauce? That's a fine question. Let's see.
Yeah. We do have another one that came in too, but I will wait and ask you that one when you have gotten to the point where you need to answer Charles' question.
All right, Charles. Maybe we covered this in the last one, maybe not. This heat pump is different. So the Mitsubishis, the variable speed heat pump manufacturers out there have the ability to vary the speed of the compressor, which is really cool, right? And they mass produce these compressors to the point that they're becoming more and more cost effective. And it's the same technology that's in full VRF systems, but a conventional heat pump compressor has this center body and it has this suction cylinder over here. Kinghome, and they don't really like talking about this, but let's just have some fun. They have this other cylinder over here. And so what they're going to do is, let's see, let me back up here. In the earlier slide, I showed you how that heat pump is trying to pull heat from the outdoors to boil the refrigerant in the outdoor unit when it's actually the condenser evaporator. So we're boiling refrigerant with -10, -15 degree, and that pressure that we create by boiling with cold temperatures drops. So that's problematic. So let's say our suction pressure, because it's cold outside, this is dropping, but we're trying to maintain a high discharge to do a good job of heating the space. What happens is the compression ratio between the discharge and the suction gets really high. So what, Tom? Who cares? Well, when that ratio gets really high, the compressor gets really, really hot. And that's why manufacturers are forced to shut down their compressors. They won't continue to work. So what Kinghome has done is they will take some of the discharge pressure through a four-way valve and redirect it into this mid-pressure jet and sort of blend the pressure from the low inlet side coming from the outdoor unit and in this bypass to maintain a compression ratio, the difference between the inlet and the discharge on this compressor. so we don't get hot. So what does that mean? The compressor never sees a really ridiculous compression ratio, so it just keeps running and running and running. So the amount of mid-pressure jet is controlled by that four-way valve, which is controlled by the microprocessor. But because they can make so many of these compressors and microprocessor boards, it's really not a big difference in cost. How did I do? This compressor looks different from everybody else's. Now, someone can copy that for sure. This is not like revolutionary refrigeration technology. Usually these bypasses get put on in the field, not at the manufacturer level.
Okay. All right. Well, Charles responded, gotcha. So
thanks, Charles.
Yes, thank you for your question. All right. So I got a question here from Nathan. Does Kinghome have an option to install the EVAPs on the heat pump? And then clarify that to say multiple evaporator.
Like a multi-zone unit?
Yes.
Okay. Let's go to another one.
All right. And yes, if anybody else has any more questions, post them in chat or pop them in the Q&A and we will get to them.
Are you seeing this, something that says configuration 2, outdoor unit,
Yep.
multiple beds and indoors? Okay, so this unit is it's a pretty slick unit. Same compressor inside, but it's got multiple ports that can, let's just use you've got a 3-bedroom and a main room. You can put 4 units, 1 in each bedroom and 1 in the main. They can look like these wall units. They can look like fan coils, I think. They can look like consoles on the wall. So this would be an ultra heat multi-zone unit. And it goes up to, I think, 4 tons. So it's pretty big, but same compressor inside of it, just piped in a different fashion. So yes, we can do that.
Okay, awesome. All right. Does it heat and cool simultaneously?
Oh, that's a great question. The answer is no. It's only in one mode. There is, and it's not in any of my presentations, Gree makes a 5-ton single-phase VRF. I'm not sure, but I think it's still heat pump mode. Mm-hmm. So whoever asked that question, and it's a good one, there are VRF systems that have, what is it? Heat pump mode or heat recovery modes. And in the heat recovery mode, it will do let's say you're in a big building, one side requires heating and one side requires cooling. Mm-hmm. It will share the refrigerant on both sides of it through a branch box or anyways, I could go, that's a whole other subject. No, not in this particular lineup. Gree does make 3-phase VRF systems as well.
Okay. All right. So Nathan, that might be more of a conversation than we have time for here, but yes. All right. Thank you so much for that question. We appreciate it. All right. We have a question from Larry. For a new home or a multifamily building, have you researched gas connection costs in Wisconsin, Minnesota, and Michigan?
Oh, man. Hang on.
Well, you have got your charts today.
Wait a minute. No, I'm having trouble managing my way through this one. Here, I just have to stop sharing for a sec.
Okay.
Where is that one? We did, so unfortunately or fortunately, I don't know, we got an opportunity to look at this Journal of Communications building with a contractor. So it was designed with furnaces, and we said, hey, we could do this all with heat pumps. And they're like, oh, really? That sounds crazy. Let's give it a look. So I'm going to have to share my, let's see, let me go to slideshow. Otherwise, you won't be able to read this. Okay, so we looked, they had a very basic furnace specified and a very basic air conditioner specified. So we compared costs. Now, granted, this is like a year and something ago, so all the costs have changed, but the principles are the same. Our heat pumps cost more by the tune of about $85,000 for this facility. It looks like there were 93 units, but the natural gas, you know, if you recall, we got multiple stories, right? So we have to run natural gas to each one of those units, and we have to run the vents out of each of those units to the roof. There was also we would have needed to build a bulkhead because usually the furnaces are in the center of the room, so you need somewhere to hide the vent piping out. So between all those costs, it was more than the difference of the cost between the heat pumps and furnaces, and here's labor. Now, because we didn't design it initially, the electrician kind of hammered us with what it cost to change from a 120 volt outlet for the furnace to a 208 volt and a little bit of a trim heater. There was some rebates for having a heat pump. I think this rebate has gone up since, but after it was all said and done, we were about the same cost. But the owners, whether you look at it as the tenants or owners or the facility owner, got a higher efficient system. They're producing less carbon footprint by having efficient heat pumps, and they got really simplified the job, got rid of all that plumbing work for the gas lines. And, you know, vent lines are kind of, let's see if I can find this picture here. Yeah, here's that shaft that you need to fill up with all your, you know, the architect has to leave a shaft for all these vent pipes. And that's just all of our products combustion from all of the furnaces. All right, Eric, bring it on.
Wow.
What's next?
Wow, that
yeah, there's that roof, right? Look at all these roof penetrations you have to make for vents.
yeah.
Or you can have them on the side of the building. Doesn't that look fantastic?
Oh, that looks great. That would look really great on that old Journal Sentinel building.
Who doesn't want that?
Yeah.
That's because these are high efficiency furnaces where the product's combustion condense to make them more efficient, but then they freeze in the outlet and then they drip down the side of the building and then you get that.
Yeah, that looks great. That would be awesome. All right, so let's move on here. We got a couple more questions. Let's see. So Dustin, not counting recent natural gas price increases, heating with natural gas costs about 4 times that of electric. With a COP of less than 4, wouldn't it always be less expensive to heat with natural gas?
The switchover point is kind of what I showed you in the earlier. Hang on. Let's see.
I guess out there, we'd appreciate a yes or no question, just one.
It's almost, look, natural gas is so cheap. It really is just hard to compete with. But if we don't, you know, hey, heat pumps would go a lot faster if we had a carbon tax or if there was some kind of tax by government. But heat pump or natural gas is mostly subsidized. The break-even point is it's not 4, but I think it's in the 3s because the heat pump is operating on variable speed, and it just really requires very little output to produce heat at, you know, in the 40s into the 30s.
Mm-hmm. Okay. All right. You switched screens. You got rid of my.
Oh,
it's okay.
Sorry.
That's okay. Well, we got it. All right. So here we go. Is there any desire to move towards a CO2 system or alternate refrigerants with lower boiling temperature for our lower temp climates?
I don't know.
Okay.
I'm just peddling what we got.
That sounds interesting,
though. The only thing I do know of is that some of Gree's products have been changed from R410A to R32. I think it's R32, R23 or R32. One of the brands that's like the higher efficient 1-to-1 is R32.
Okay. All right. So we got Larry said CO2 is currently being researched by some
Oh, that would
major
be Larry, my
manufacturers.
brother. Thanks, Larry.
All right. One more. It looks like the 15-year savings in energy would have been close to replacement costs if the units had a 15-year life expectancy.
I would expect the units to live 15 years for sure.
Mm-hmm.
The trouble with almost all multifamily buildings is, look, the tenant pays the bill. The same is true for non-owner occupied buildings. I occupy the building that we're in now, so putting in a solar system, which I did, I get the payback for it, so I can make the investment. If you're not paying the utility bill as the owner of the facility, what motivation do you have to make the systems more efficient? Well, it benefits your clients, but I don't know how most people are looking if they're looking for an apartment, it's not what's the cheapest utility I'm looking for. It's somewhere down the list. I mean, maybe they pay attention to it, but I would imagine it's what's the floor plan, what does it look like, and what's the location. And then if it happens to be very efficient, maybe. Although I think our younger generation is getting a little more sophisticated, and maybe they're looking at that with wider eyes.
Okay. All right. And with that, we have reached the end of the questions that we've received. So Tom, thank you again for putting this together and doing this. This was a lot of fun. Everybody, if you do have any questions besides the ones that were asked today, and you'd like to reach out to Tom, you can go to
airflowreps.com.
Yes, airflowreps.com, or go to allseasonheatpump.com and just click the contact us button, and we'll get back to you. Thank you, everyone. Have a great day.
Thanks everybody for hanging in there.
Thanks, Nathan. Nathan said, good subject. Thank you, Tom.
Thanks, Nathan.
All right, you guys take care.
All right. So long, everybody.